Hello everyone, thank you for joining the presentation. My name is Aral Hekimoglu. Today I will talk about our paper titled Active Learning with Task Consistency and Diversity in Multitask Networks that we wrote together with two of my supervisors, Schmidt and Alvaro Marcos-Ramiro. First, I would like to give a bit of an overview about the problem and our motivation for the paper. We all know that multitask learning is quite important, but it needs a lot of labeled data, and labeling it can become quite tedious when we have a lot of tasks at hand. Therefore, a good selection strategy is important to decide on which of the unlabeled samples to label. One key question is then how to utilize the inconsistency between the multiple tasks and information present in multiple tasks to guide the selection of which data to label. Which brings us to the multitask active learning problem. And in this problem, we observe that using task interactions and using the diversity of multiple tasks is quite underexplored. The first selection criteria that we can use is the task robustness. In the recent multitask networks, the MMD block or the multimodal distillation block is used to refine initial task predictions shown on the left to have refined task predictions shown on the right. So what we observe is that tasks with inconsistent predictions between the initial and the refined prediction actually lack robustness. And these tasks need to be labeled and trained with these interesting samples. Therefore, we propose to use the discrepancy between the initial and the refined predictions of these two-stage multitask network as a selection criteria. Another important criteria is using the diversity in the multitask setting. In single-task active learning, diversity is used to create a diverse set of scenarios. However, it's still underexplored in the multitask setting. So here we propose to gather the diversity information from multiple tasks to guide the selection of data for labeling. So instead of focusing on the whole image, we propose to look at the predictions of each task and then use the information from those tasks to define the diversity. So for example, here on the left, we have the diverse sample shown as the red selection, which includes an interesting scenario. For example, people wearing motorcyclist helmets. And as you can see, the segmentation is not that good in the helmets, and this proposes a unique challenge compared to the sample on the left, which is a similar sample with just having people in the group facing the camera. So we propose a multitask active learning framework. So first we select some samples on the unlabeled pool. We define two different selection scores and have a combined score. So the first score that we have is the inconsistency score, and we have the diversity score. And then we select the samples with the highest combined score and send them for labeling and then add it back to the training set. Then we modify the multitask training a bit with scaling based on the selection scores so that we also maintain the single task active learning information during our training when we have multiple tasks. So as our selection score based on the inconsistency, we first propose to construct a committee of predictions. So here on the left, we have the depth estimation predictions. And we refine these depth estimation predictions with the segmentation, with the edge detection, and so on. And then we have these committee of refined predictions. So each of these are pairwise refined predictions for the task of depth estimation. Then we calculate the inconsistency score as the loss between these pairwise predictions, between the initial and the refined task predictions. And we take the maximum of the loss to define a single score. We do this for every task, which gives a score separate for each task. To define diversity, we need a vector representing a sample so that we can calculate the distance between samples more easily in this vector space. So for this task, we propose to use the task-specific hats and features from these task-specific hats shown as different colors here, and we combine these features into a single unified representation. However, this unified representation is a high-dimensional vector, And it can also contain some information multiple times. For example, for the edge, for both the depth and the depth estimation and edge detection, the same edge can be incorporated in this information multiple times. Therefore, to summarize it and to reduce dimensionality, we use an autoencoder structure that takes these combined features, encodes it, and then decodes it back. And we use the mean square error loss to train this, which gives us then at the output of the encoder the encoded vector. Then, along with our inconsistency-based selection score, as we described before, we define a new score which is based on the diversity. And here we use the encoded feature vector of samples and their distance to the training set or the samples in the training set, and we take the minimum distance, and this gives the diversity of the sample. Then we combine the diversity-based selection score and the inconsistency-based selection score by multiplying those two and into a unified single score. After selecting the samples based on the selection score, we send them to the labeling and add it back to the training set. However, we have a dilemma here where the selection score is specific to each task. However, the labeling has to be concluded for all tasks simultaneously. Therefore, we lose the principles of active learning, because for some tasks, the selection was not that important, but it was labeled because it was selected for another task. Therefore, we need a way to scale the training of each task and each sample by that task selection score. Therefore, we propose to modify the multitask weighted loss function by an additional score or a term which is based on the selection score, which is shown as sk of x. So here for each sample, we have the loss multiplied by the task's weight multiplied by the task's weight for that sample. We validate our results on two datasets, the Pascal and the NYU, and we have active learning curves for all of the tasks, but also the multitask loss, which we define as the multitask performance. So here at the top left, we show the multitask loss, and here we observe that our method is able to reduce the loss by 8.5% more compared to the other baselines. And we also reached the loss of the fully trained model with only using 42% of the data, which corresponds to using 6% less data with respect to the second-based active learning method, which is part AL. And also on the single task methods, we observed that our method for most of the active learning scenarios can outperform both the single task baselines, but also the multitask baselines. We observe similar results on the NYU dataset, where we show 2.8% more reduction in the loss compared to the state of the art. And also we reached the loss of the full trained model with only using 50% of the available data. We also show some qualitative results, where on the left we have a diverse scenario with a wedding dress and we are able to better segment it. And on the right, we show that the inconsistency in the segmentation of the sailor's head is much more smoother in our case. So in conclusion, we proposed a multitask active learning framework with a coherent selection and training strategy. In our selection strategy, we propose an inconsistency-based selection score, where we leverage the inconsistencies between the initial and refined test predictions in the multitask refinement networks. We also propose a novel feature embedding approach that is specifically tailored for the diversity-based active learning in the multitask setting, where we are able to capture the task-specific characteristics, but also we can condense them into a unified feature vector. Then, to keep the dynamics of single-task active learning during training of a multitask network, we propose to use a loss weighting strategy, where we adjust the impact of samples based on their selection scores. This results in state-of-the-art performance in active learning, where we are able to reduce 8.5% more in the multitask loss